MT Series 2 for NTA NET Electronic Science and PSUs. Now, the probability that an electron in a metal occupies the Fermi level at any temperature is, as we know that Fermi level, if the EF denotes the Fermi level, then Fermi level means the 50% probability of occupancy by electrons, okay, and it actually gives the information about the velocity of electrons that participate in electrical conduction, okay. So electrical conduction. So if I talk about metals, in metals, the probability that an electron in a metal occupies the Fermi level at any temperature is F of E is equal to 50 is equal to 50%. Okay, as I have already told you that all energy states above Fermi level are empty and all energy states below Fermi level are occupied by the electron. Okay, now in case of insulators, if I talk about, then in insulators F of E is equal to 0 is equal to 0%, means this is the probability that an electron in an insulator occupies the Fermi level at any temperature. In case of semiconductors, the probability that an electron occupies the Fermi level at any temperature is F of E is equal to 50 is equal to 50%, or you can say answer is 0.5. I'm sorry, here it is not, it is actually 0.5. okay, it is 0.5. Next question, the drift velocity of electrons in silicon, as we know that drift velocity is equal to mu E. Okay, that means it increases linearly with electric field at low values of electric field and gradually saturates at higher values of electric field. In the previous slide, I have shown you the graph like this way. Okay, this is mobility versus electric field, volt per meter or volt per centimeter, whatever unit you want to take. And the graph is like this. Always remember, this is very important graph for gate point of view, for any PSU point of view. Okay, so in this graph, this is the region where mu reduces to 1 by under root E, and this is the region where mu is 1 upon E. So when Vd is equal to mu E, for low values of electric field, this mu is kept constant and this drift velocity increases linearly with electric field, okay, and gradually saturates when Vd is equal to mu E. When E is increasing very high, then mobility reduces gradually and this drift velocity saturates. So this is the answer. Next question, a p-type silicon sample has a higher conductivity than an n-type silicon sample having same dopant concentration. This is actually false statement, because as we know that mobility of electrons is always greater than the mobility of holes. Okay, so unit of mobility is, always remember, meter square per volt per second or centimeter square per volt per second. Sometimes in net exam the unit is also asked. Okay, so sigma, which is conductivity, this is equal to Qm mu n. If this is sigma n, conductivity for electrons concentration, and this is sigma p, conductivity for hole concentration, Qp mu p. So we can say that this sigma n is directly proportional to mu n, this sigma p is directly proportional to mu p. As we know, this is always greater than this. So how can this conductivity can be greater than n-type silicon sample? So sigma n is always greater than sigma p. Conductivity of n-type is always greater than conductivity of p-type. So this statement is false. Next question. A silicon sample is uniformly doomed with 10 to the power 16 phosphorus atoms per centimeter cube, that is MD. We have given donor concentration, okay, remember, atoms per centimeter cube. Now boron, we have given boron atoms, means acceptor concentration. This is 2 into 10 to the power 16 atoms per centimeter. As we can see, this Na is very much greater than ND, This is acceptor concentration, this is donor concentration. So here we have if the dopants are fully ionized, it means that the material will be p-type, because as the question already says that Na is greater than Nd. So p-type with how much concentration? Na minus Md, that is nearly equivalent to 10 to the power 16 atoms per centimeter cube. So the right answer is this much. P-type will carry a concentration of 10 to the power 16 per centimeter cube. Now last question, the units of Q by kT. This is very important. Always it is asked in UGC net exam. See, d by mu is equal to dn by mu n is equal to dp by mu. Very important relation. This relation is called Einstein relation. Okay. So this is also equal to kT by Q, which is Vt, which is T degree Kelvin upon 11600. So Vt is a thermal voltage. What is this? This is thermal voltage. This is equal to Q by kT, whose unit is volts. Sorry, whose unit is per volts. If I talk about, because this Vt is equal to kT by Q. So this unit is volts, but if I reverse it, on reversing this, we have Q by kT is equal to per volt. So answer is per volt. So thanks. In the second PPT, I want to apologize because in that slide I have mentioned the wrong unit of H. I have shown you H is equal to E is equal to h square k square upon m square. This is actually, this h is Planck's constant. Okay, this is Planck's constant, which is equal to 6.62 into 10 to the power minus 34 joule second. I have actually mentioned the wrong unit, joule per degree Kelvin. Actually this joule per degree Kelvin, it is of K, Boltzmann constant. This is called Boltzmann constant, 1.38 into 10 to the power minus 22. So I'm very sorry that in the second slide I have mentioned the wrong unit of Planck's constant. Thank you. Please like, share and subscribe. Thank you.